Hi, welcome to the introduction to gradient boosting. So today I'm going to talk about additive modeling. I'm going to talk about the gradient boosting for regression with mean square error and gradient boosting for regression with which is the absolute error. So first, let's review what we know about AdaBoost from the previous videos. So in AdaBoost, we have a data set x1, xi, yi, and we're basically gonna train initially our model on the data set the way it is, which is equivalent to training with uh, uniform weights. So for example, out of that training, we get a decision tree, okay? Now that decision tree made some mistakes, right? So it basically fit the model well in part of the data and made some mistakes. And what we want to do is that the next decision tree will concentrate more onto the examples that were misclassified by the first decision tree. So in order to do that, we increase the weight of misclassified examples, okay? And we continue doing that. So basically we take our data set and keep changing the weights of the misclassified examples according to what the model have done so far, basically. So in this model, the trees are not independent as in random forest. So in this model, the trees depend on each other. So, and they are trained sequentially. Okay. And then finally, once we have, M trees, we're going to combine that trees by weighted voting. So we're going to weight each one of the trees, and the weighted sum is going to be our model. Okay. In particular, this is the formula that we use for binary classification. So in binary classification, we consider labels to be +1 or -1, and we use as the prediction to be the sign of the weighted sum of these classifiers. Okay. So we call this additive modeling because our model is a sum or a weighted sum of other models. So let's think about some intuition around additive modeling. One way to think about additive modeling is that each model itself is an expert. For example, in this particular example, you have an expert that looks at income, and an expert that looks at credit history, an expert that looks at savings, and an expert that looks at market condition, right? And given a particular observation, we're gonna figure out if we're gonna give this person a loan or not based on all these variables. So if a expert is gonna weigh in and is gonna say, oh, I will give a loan, I would give a loan, I would not give a loan, I would give a loan. And each one of these experts is gonna have a weight. And we are gonna give our final prediction. It will be the weighted sum of these experts, and we're gonna kind of look at it and decide based on that. Another possible way of thinking about additive modeling is about a decomposition of a very complicated function into simpler terms. For example, we have this function here, right? So, and you may think about right away that maybe there is a bias term, maybe there is a trend, right? And there is something else going on, some kind of noise, right? Maybe a sine or cosine function going on there, right? So this is a very simple example, and I actually can tell you what the function is because I created a function. And so that function is a sum of simpler functions. One is a constant function, the other one is a linear function, and the other one is a sine function. But suppose actually we didn't know much about this particular function. So we have this, our first function, and then we say, well, let's actually try to find the best constant function that we can find, and we find that, a 5 maybe, and we subtract from the original function, we subtract the 5, and that's going to be called a residual. And then we put our residual into another model. For example, the model may try to find the trend, right? And then we find the trend, which is like 2x maybe, and we subtract that from our original y, and we get another residual, and then maybe we feed this residual to another model. Okay, so that's how we're going to think about gradient boosting. We have some original y's, right? We're going to find one first model that is going to feed that data, a simple model maybe. We're going to take a residual, and we're going to send that residual to another model that is going to feed the data, and we're going to keep doing that. And basically the second model is going to try to kind of look at the places where the first model didn't do very well, right? And so on. This third model and so on is going to try to basically look at the places that the previous models haven't done that well. Okay, so to correct basically. So let's actually do this in a very small example first to get an idea of how this is done. So suppose, so I have this data here, which is a tiny data set on the price of rent of a house based on the square feet of that house. Okay. So basically, what we're gonna do first in this like regression boosting is that we're going to find the best constant that we can find. In this case, the best constant is gonna be the mean. Okay, so this column F0 is the best constant, which is the mean of all of these rent prices, right? And then we're gonna compute a residual. Residual is gonna be square feet, the y that we have, minus the constant function, right? And that residual is gonna be this new column that I'm giving you here, okay? And now what we have to do is to find, because it's gonna be trees, we're gonna start fitting trees, right? We're gonna find the best stump that fits this particular data here, and we're gonna do this by hand. So we're gonna do together this example in which we're gonna try to first compute the T1 is the stump that fits this data the best, okay? Then we're gonna compute F1, which is our constant F0 plus our new tree T1, okay? And then we're gonna compute the residual again. Okay, so I have a little notebook that you guys can open, and we can together try to do this together. Before doing that, let me remind you how we fit a tree. Okay, so suppose we want to feed a tree to this particular data. So we have the square feet and the rent. Okay, so and suppose that we split in 850. So we split such that everything that is below 850 goes to one node, and everything bigger or equal than 850 is another node. So what is the prediction of this particular tree? If you remember, the prediction of the particular tree is going to be the average in each of the nodes. So in this case, it would be 1180 for the first two observations, and it's going to be 1343 for the other observations. Okay, so also, how do we compute the mean square error of this prediction? Okay, remember, mean square error is y minus prediction square, right? And the sum over all of those observations, right? So we have to compute the errors on one part of the tree, compute the errors on the other part of the tree, sum them, and divide them by the total number of points. Okay, so let's go and do that. In our case, we are not fitting rent by itself, we are actually fitting the residual, right? Okay, let's do that. So I have my notebook here. So in this notebook, I have my y's already here. We have the mean of y's, which is this f0 that I have here, right? And we have our residuals, which are these numbers that I already populated here, right? So, and I have a little function here that, given an array y, is gonna give me the sum of errors, basically. So I will take the mean, which is the prediction, right? And I will subtract the y from the mean, and I will square, and I will sum all of these errors, okay? This is a function that is gonna be useful for you to be able to find the best tree. Okay, so I have 5 points, right? And they're already in order because that's kind of handy, right? So basically, one way to think about how to find the best tree is to try all possible trees, stumps in this case, that we can have. So since we have like 5 points, we have 4 splits we can have, right? So for example, we can split in the middle in between two observations, and that would be, in 775, 825, 875, and 925. Okay, so how do we think about, so these are the residuals, right? So if we split on, for example, 775, we're gonna have two nodes. The first node is gonna just have the first number, right? And the second node is gonna have all of the other numbers, right? And this is actually true because the x square feet is order, right? Otherwise we will have to do more complicated stuff. But in here, since everything is in order, then it's kind of easy to think about it that way, right? So the y's, which are these residuals, are also in order. So basically what we have to do is to compute the error of this particular split, right? So the sum of errors of the first split, we know it's going to be 0, right? Because it's just 1 point. The mean is just the value on that point, so the error is going to be 0. But just in case, we can just just make sure that this function here is going to give us a 0, so we can compute this sum of errors, 0. Perfect. Sum of errors here, this number, right? And the sum of error of the whole split, I claim that we just kind of sum, and then we can divide by, there are 5 points, so we divide by 5. So that is the MSE of that split. Okay, so similarly, we can just compute the MSE of, just basically by doing like, I equal to, and then do I here and I here. We compute the MSE of the second split, and then we can compute the MSE of the third split. And finally, we compute the MSE of the last split. Okay, and it looks like the last split is the best, right? Which actually makes sense, because if you guys look at this, you see that this number is very big, this 580. So basically it makes sense that it will kind of split around here, and it will leave 580 by itself, and it will put together all the other guys, right? So now, what is T1 exactly? So if we split here in say 925 in the middle here, right? So what is going to happen is that T1 on the last point is going to be 582, right? And on the other point is going to be the mean of all of these residuals here, right? So let's compute T1. Our vector itself, T1, is going to be, basically, so let's actually try to figure out what's the mean of So you have this. These are the first 4 numbers, right? And we figure out the mean of these numbers. Okay, so that's kind of, so T1 is gonna be, 4 times so for this minus 145. Okay. So wait, sorry. It's just gonna be four times this number and then finally the last number, right? So the number 582. Okay, so that's gonna be T1. Okay, and then what is gonna be then in this case F1? So F1 is F0, the mean, plus T1. So we have F0 here, which is the mean, y the mean, right? So we're gonna have F1. F1 would be like the our prediction after one step, or depend 2 steps, depending how you think about it. But I think about it as one step. So this F1 is gonna be our function so far, right? And then basically to get the next 3, we're gonna compute the residual again. So this is the function we have so far, this is approximation so far. So we're gonna take y minus F1, and this is gonna be our new residual, okay? And then we're gonna have to basically again figure out what is the best split that we can have to divide these 3. To divide this residual to get a new stump, to get a new f. So okay, I hope that you understand how to compute this T1, the F1, and the y minus F1. To get your understanding better, try to do another iteration. Compute T2, the next 3. Compute F2. Compute y minus F2. Okay, cool. So let's go back to our lecture here. So basically, let me tell you what is in general gradient boosting for the square loss function. Okay, so we initialize our model with the mean of the y's. Okay, then we compute a residual vector. So for every point in our data, we take our current model, which in this case is the mean, and subtract that from y. So we do y minus our current model, okay? And that will give us a residual vector for all observations. And then we feed a regression tree to the residuals, and that will give us a tree, right? And then we update our current model using the previous model plus the new tree. Okay, and at the end we return the sum of all of these models. So that is gradient boosting for the square loss. Okay, so gradient boosting is a more general algorithm that can be used with any loss function. So what I'm gonna do next is I'm gonna show you the model for the absolute loss, and then in the future video, I am going to show you in general what is the gradient boosting algorithm. So actually I have here for you some plots on how this how the algorithm works. So in terms of the residuals, which are the blue points, and the actual models that you are feeding, which we call F, but in this picture is called delta. Okay, so you can compare this with the table that you just computed. So the algorithm for the mean absolute error is a little bit different. It has a similar style, but a little bit different. So what we do here is that to initialize the model, instead of using the mean, we use the median. And you may want to think, why is that, right? Remember that the median is the best constant that minimizes the mean absolute error. Okay, we talked about that in a previous video. So what we do right now is that we, the first thing we do is that, we compute the median of all of our targets. The second thing we do is that we compute something that we call a pseudo residual. So you actually compute the residual similarly to what we did in the previous version of this algorithm. But then instead of just keeping the residual, we take the sign of the residual. Okay, then we feed a regression tree on the targets, on the residual targets. Okay, but after we do that, we correct the predictions of these. We correct the predictions. So the prediction that you would have gotten was the mean on the terminal nodes. So instead of using the mean on terminal nodes, we're going to use the median. Okay, and then basically we just update our current model by summing the new tree that we have, and we return the sum of the trees. So this is a little bit tricky here because we are kind of using kind of the same ideas from the previous algorithm, but we are instead of keeping the predictions that the regression tree will give us. Remember, the regression tree will give predictions that are the mean. But for the means absolute square error, what makes sense is the prediction is the median. So what we're going to do is that we're going to correct that to give the prediction that makes more sense for this loss function, right? And then we're going to keep that tree, but with slightly different predictions. And after that, we basically do the same. We just basically have this tree, and we add the tree to our current model, and we keep until we, until we have M trees. Okay, and the model returns the sum of all the trees. So here I have an exercise for you in which you have to do the same thing we did before, but now would be with this algorithm instead of the mean square error. See you in the next video.